Yes, if something is a function, that means x doesn't repeat. If I put in an x value, I get the same y value every time. I don't get different y's out. If it's one-to-one, two different inputs give you two different outputs. Another way of saying it is if you have two different x's, they can't give you the same y. Or another way of saying this is y never repeats. So in a function, x doesn't repeat. In a one-to-one function, y doesn't repeat either. So first, let's decide if things are one-to-one. We saw these, we did some of the same types of problems when we were dealing with trying to decide if something was a function or not. Would this first one be one-to-one? No. No. Why?
30.
Is this one one-to-one? Yes. Yes. If I look, my y value, 6, 3, 2, 5, 8. Y never repeats. Okay, if we are stuck with an equation instead of a mapping or a set of ordered pairs or a graph, we have to have another method, an algebraic method of deciding if it's one-to-one. We can't just say plug it in your graphing calculator and look at the graph because we don't have graphing calculators. So we have to understand what it means. If y never repeats, then if I put in two x's, I have to get two different y values out. So what we'll do is we're going to put in two different x's. We'll do an a and a b. And we're going to pretend their y's are equal to each other. If you put in those two things and their y's are equal to each other, we're going to work it out and see. If it tells us that a has to be equal to b, that means it's one-to-one. Otherwise, it's not. Sounds really complicated, but let's look at it. So one-to-one says y never repeats. So if I want to decide if y repeats, we're going to pretend it does. We are going to pretend that when you put in an a and when you put in a b, those y values are the same. So f of a would be negative 3a plus 7. F of b is negative 3b plus 7. Now I want to solve this for a. So what would we do? If we divide by negative 3, we get a equals b. So we started out and said, okay, pretend we got the same y twice, and what it told us is the only way y repeats is if you plugged in the same number to begin with, if a and b were the same number. So that means this is one-to-one. A lot of times I just do 1-1 to show it. So this is the definition of one-to-one. Let's look at this one. So if it's one-to-one, that means y can't repeat. So we're going to start out pretending y does repeat. F of a is equal to f of b. Okay, so if you put an a in, we get the square root of 49 minus a squared. If we put in a b, we get the square root of 49 minus b squared. Take a second and solve this for a. See what you get. Square root. Square both sides. The opposite of a square root is a square, so we could add a square on each side. So 49 minus a squared equals 49 minus b squared. Subtract our 49, so negative a squared equals negative b squared. Divided by negative 1, a squared equals b squared. How do you get rid of a square? But if you add a square root, what else do you have to put? So A could equal positive or negative B. What that's saying is, if I put in 7, for instance, I get the square root of 49 minus 49, so I get 0. If I put in a negative 7, I get 49 minus 49, so 0. A positive and a negative give me the same y value back. Is that 1 to 1? No. So this one is not 1 to 1. When you solve it, if you get A equals B, that means it's 1 to 1. If you get anything else, and typically it will be a plus or minus that causes the problem, then it is not 1 to 1.
Okay.
You add the square root into the problem, that's when you have to put the plus and minus. So something like a square makes a function not 1 to 1. In terms of a graph, if we're looking at a graph, how do we decide if something's a function? Vertical line test, because x can't repeat. So how would I decide 1 to 1? Horizontal line test. If a function is 1 to 1, then every horizontal line can intersect at most once. So if I wanted to use that, if it's one I know the graph of, so I can't just use my calculator, but if it's one I know, then we can use the horizontal line test. What does x squared look like? A parabola. Does that pass the horizontal line test? No, you can draw lots of horizontal lines that hit that more than once. So that one is not 1 to 1. What's x cubed?
Chair.
Okay, does that pass the horizontal line test? Yeah, no matter where I draw my horizontal line, it's only going to touch my graph once. So this one is 1 to 1. So it's really nice if we have a graph to look at. Very quick to tell. Otherwise, we're stuck using the f of a equals f of b. Any questions on 1 to 1? If we ever have a function that's always increasing or always decreasing, then it will be 1 to 1. Think about it. If you have something that's always increasing, no matter what else it's doing, it's just always going up. That has to pass the horizontal line test. Likewise, if it's always decreasing, it will pass. It's when you change directions, when you go from increasing to decreasing, or vice versa, that it creates problems. So if it's always going up or always going down, it would automatically pass the horizontal line test. Now we care about 1 to 1 because if a function is 1 to 1, we can find the inverse, which is our big goal with this section. Inverses are what happen when you flip x and y. The reason it has to be 1 to 1 is if it wasn't, and you flipped x and y, you would no longer have a function, because then x would repeat. So it has to be 1 to 1 in order to find the inverse. The symbol for inverse is just a -1. It looks like a -1 exponent, but it has a different meaning. It's not truly acting as an exponent, it means the inverse. So, if I asked you to find the inverse of just a set of ordered pairs, all I've told you about the inverse is it flips x and y. Doesn't change any signs, just changes the order. So my first order pair would be what? The second one. Third one. Fourth one. Fifth one. Oh, I left off one more. Eight, 2, and my last one, 27, 3. All right, you guys do B. Write down the inverse of that.
2.
Okay, so if we have ordered pairs, it's easy to find the inverse. We just flip x and y. If you look at this, the domain of the original one becomes what in the inverse? the range because the x's become the y's and vice versa. So the domain of the function is equal to the range of your inverse. The range of the function is equal to the domain of an inverse. Also, an inverse is like the opposite of something. Okay, it undoes an operation. So if I say x plus 5, what's the opposite of adding 5? Subtracting 5. What happens if I take a number and both add 5 and subtract 5? I get the same number back. So if you have inverses and you do both, you should get your original back. So if two functions are inverses, when you compose them, you should just get x back. All right, so using that, let's decide if these are inverses. If they are inverses, it means that they have to undo one another. So when I do f composed with g, what should I get for my answer? Should get just x back. Have to get back what we put in. All right, so if I do, so f of x cubed, so remember when we do the composition, we start on the inside. G of x is x cubed. I have to go to f, and that replaces my x. So function f is the cube root of whatever I put in, and I'm putting in x cubed. What happens if you do the cube root of x cubed? You get x. Now, it's not enough to show just one of them works. We really have to check both. So compositions, order does matter in a lot of situations. So I need to also check g composed with f and show that I get x for that one as well. So if I do that, starting on the inside, my inside is f of x. What is f of x? Okay, I'm going to put that into g. G is whatever I put in cubed. So if I put in the cube root of x, the cube root of x cubed is x. Both of these came out to be x, so that means they are inverses. When you do both operations, they cancel each other. What if I did one of them and I didn't get x? Would I have a need to check the other? No. If one of them doesn't work, then I don't have to verify the other one. I can just say they're not going to be inverses. Let's do another one together. So if I want to check if these things are inverses, so f composed with g. That's f of g is 1 over x minus 1. I am going to put that into function f. So function f is 1 over so whatever I'm putting in for x minus 1. Okay.
Oh, because it's just random.
Okay, so if I combine like terms, I have 1 over x minus 2. So we did these compositions earlier in the semester. Do you guys remember doing them? You always start on the inside and work your way out. Okay, from this point, it's kind of ugly. I need to see if I'm going to get x out of this. What I'm going to do, in a fraction, it's legal to multiply both the top and bottom of the fraction by the same thing. Okay, I'm going to take top and bottom times x because I have an x in this denominator. We don't usually write a fraction within a fraction. If I do that, 1 times x is x. On the bottom, what is 1 over x times x? 1. Minus 2x. Is this giving me what I need? If they're inverses, what does my answer have to equal? X. Am I getting x here? No. So is there any reason to check the other one? Nope. I can stop and say these are not inverses. They did not cancel each other out. It'd help if I could spell though. Okay. I want you guys to try this one. So take a minute, see if you can figure out if these two are inverses. We have to check both compositions. If they both turn out to be x, they're inverses. Start on the inside. G of x is 1/3 times x minus 4. I'm putting that into function f. So f is 3 times whatever I put in plus 4. Now there's different things you could do from here. You could distribute the 1/3, or you could multiply. What's 3 times 1/3? 1. So it gives me x minus 4 plus 4, which is x. So that one worked out, but I have to check the other. So we have to check the other one as well. So that's g of f is 3x plus 4. So I'm going to function g, and I'm replacing this x with 3x plus 4. All right, so different places you could start, but if I just work on the inside, 3x plus 4 minus 4 just gives me 3x, and 1/3 times 3x, x. So these are inverses. So if one works, you have to check the other one. If the first one doesn't work, you can stop and say they're not inverses. All right. Do we have questions on checking to see if functions are inverses? So, graphing wise, because inverses flip x and y, the graphs are always symmetric across the line y equals x. And I think Mrs. Keller was really good about when you guys found inverses. She always had you graph that line y equals x as a dashed line on your graph, and you graph the inverse and check, is this the same on both sides? That is our line of symmetry. So that's a good way to check your answer. To illustrate that, we're actually just going to graph an inverse. So if I wanted to graph the inverse of the line y equals 3x minus 2. Okay, we know how to graph lines. What would I plot first? And then my slope is 3 over 1. 3 over 1. So, oh, that is a very crooked line. We can do better. So there's my line. If you graph the line y equals x, so y equals x, y-intercept is 0, slope of 1. That red line should be the line of symmetry for this graph. if you wanted to check, all you really have to do is get some points. This is the 0.11. If I reverse that, what's that point? Still 1, 1. This is the 0.0, -2. So what would be my point on the inverse? -2, 0, because we know x and y flip. So now I have 2 points on that one. So there's that line. So other than the fact that my lines aren't perfectly straight, we should be able to see that these are inverses. And again, how I did that is I took the points on my original line that I graphed. So 1, 1, and 0, -2. And we know the inverse just flips x and y. So this is still 1, 1. This one becomes -2, 0. So those were the 2 points I used to graph the green line. Okay, and we see if I fold my paper over that red line, do those two overlap each other? Yes. So when you're looking at the graphs, y = x should be the line of symmetry for them. Let's practice graphing another inverse. So to do this, I just want to look at ordered pairs. Okay, so take a few on your graph. What's this point? 1, 2. So when you do the inverse, where would your point be? What's this ordered pair? So when I do the inverse, what would my point be? What's this ordered pair? So when I find the inverse, what would my point be? What's this ordered pair? So when I find the inverse, what would it be? And if you check the line y = x, doesn't that go right through the middle? If I fold on that line, they overlap. So we can double check ourselves that way. All right. I think I'm going to stop here today. I want to hand back tests and go over questions on those, and then I want to talk about your homework. So, the homework is a handout posted on Google Classroom. We have not finished the section, so we can't do everything yet, but I don't want to overwhelm you too much on the first day. So, on that handout, trying to pull it up so I can see how much we're ready to do. All right, on this handout, you can do 1 through 15. You can't do the last 4 yet. We'll talk about those tomorrow. And so then it will all be due on Friday. So tomorrow we'll finish it, and it will be due Friday.